In this video, we're going to take the idea of a spanning tree a little bit further. So you'll notice here in this graph, which is certainly not a tree, right? I put numbers next to these edges here. Now these are not numbers as in what order I'm going around them. These are weights. This is a weighted graph. So you can think of these numbers here as distances or cost or whatever it may be. And the idea is we want to find a spanning tree for this graph that is going to have a minimum total weight. To give some real-world examples for this idea, let's suppose that this graph is some kind of map of your house and you have all these computers or other devices connected to the internet. Now nowadays we use Wi-Fi a lot of the times and we don't really worry too much. As long as the signal is there, we're okay with that. But what if I wanted to use actual cables, right? What if I wanted to actually have network cables between all our computers here, make it hardline, make it more reliable? This is definitely something we had to deal with, before Wi-Fi became so effective. But even nowadays, there are times when you want to do this. There are some famous stories of companies moving buildings in New York City to be a little bit closer to the stock exchange so that their internet would arrive there a little bit faster, fractions of a second, in order to have their trades go in first. So there can be definitely times when the length of wire very much matters nowadays. And so the idea is I could put wires on all of these, right? I could just wire everything and then everything's connected, but that's not going to be the most efficient way. I want to put just the fewest number of wires that will allow me to reach every computer, as well as having the smallest total length or cost for all the wires. Now there are going to be two main algorithms that will help us find these. One is called Prim's algorithm, one is called Kruskal's algorithm. They only differ ever so slightly. They are guaranteed to find the minimum spanning tree, but there are possibilities that there are going to be more than one minimal spanning tree. For example, you notice how I have a couple of edges that both have length 2. Maybe one tree that's minimal will use one of those but not the other one, and then a second possible solution will use the other one. So it's possible that there's more than one spanning tree that has the same total length, and these algorithms might find different ones there. So you might get different answers or you might get the same one, but regardless, here we are. So for Prim's algorithm, you always start by taking the smallest length edge, which in fact both algorithms are going to start the same way. So you look at your whole graph and you say which edge is the absolute smallest. In this case is 1. That is the one that we are going to use. Now that we have picked the first one, we are going to say, of all the edges that are connected to that one, what is the smallest possibility? So at this point in time, there are 1, 2, 3 edges that are connected to my starting edge here. And of those 3, the smallest is going to be 2. And so that's the one that I'm actually going to add. So I'll ignore these for now. And I add on only the edge that is 2. Then I ask myself, okay, of all the edges that are connected to the stuff that I've already done, what is the smallest of them? So I see a 5, 2, 5, 7, 6. That means the 2 is going to be smallest. So I go ahead and add just the 2 here. Then again, I ask myself, okay, at this point in time, of all the edges that are connected anywhere to my graph, which of them are the smallest? And it looks like the 4 is going to be the smallest here. So I'll go ahead and add just the 4. And I'm going to keep doing this. I'm going to keep saying, okay, of all the things that are currently connected, add the smallest one. So even though I see I have a 3 up here in the left-hand corner, since that 3 is not currently connected, I am not going to add that 3. Now, without drawing all the red dotted lines here, we can just look for things that are connected here. It looks like 5 is the next smallest. And in fact, there are 3 5s here. Now, when you have multiple of the same thing, you have a choice to make. Generally, you can pick randomly whichever one you want to use. However, you do want to be careful of one thing. You do not want to break the fact that we want a tree here. So if I were to add this right one over here, this right 5, that would make it so it's no longer a tree, so I can't do that. However, there are 2 other 5s. I'm going to go ahead and add one of them randomly. You could have chosen the other 5 and that would have been perfectly acceptable. So it doesn't, you just have to use whichever one you want to do as long as you don't break the tree rule. Then if all the edges connect to that, it looks like 3 is the smallest. So I go ahead and add 3. Of all the edges there, looks like 4 is the smallest. And then of all the edges left, it looks like 6 is the smallest. That would not break that. So there we get our minimal spanning tree using Prim's algorithm. Now for Kruskal's algorithm, it's very similar. You start by taking the smallest edge, which is right here. And then you add on the next smallest edge, which is 2. And the next smallest edge, which is 2. Now notice that since they were both 2, I could have picked either one first. In Kruskal's algorithm, we don't actually care whether it's currently connected or not. We just still take the smallest one that doesn't break the tree rule. And so at this stage here, this is where things are going to change, because I have a 3 up here. I can go ahead and add that even though it's not connected. So in Kruskal's algorithm, we don't care if our new edge is currently connected to our previous edges, because at the end they all will be connected. Now at this point in time, I have 2 4s. I can choose which one I want to add. I'll go ahead and choose to add this 4 here. Then I say, okay, I have another 4. I'll go ahead and add that. Now I do want to point out something. Let's suppose that when I added one of the 4s, it made it so the other one violated the circuit rule. That's okay. This means you get the first one in there. And so it might have only gotten 1 4, not the other one. Now at this point, I have 5s. There are 3 5s I could possibly add. The same reason I can't add this bottom right one, but I could choose to either put this middle down one or the top across one. I'm going to just randomly choose that one there. And then of the things that I have left, I have 6 and 7. 6 will go there. And at that point in time, I now have my spanning tree, and it's a minimal spanning tree. Notice that it is a different tree than the previous one by Prim's algorithm. That's because in this graph, there are multiple minimal spanning trees. If there had only been one possibility, then they would have gotten the same answer. But in this case, there are multiple possibilities. And so these are our 2 algorithms. It's kind of similar to the nearest neighbor and cheapest link here, except the nearest neighbor and cheapest link, we were trying to find Hamilton circuits and get back to where we started from. Now we are trying to find minimal spanning trees. So again, it's a little bit different on our goals and our situation, but it's pretty similar in that whether we are looking for where we're currently at or whether we're looking overall. And this is what we have.